So really excited to be part of this today, and I look forward to continuing these conversations, fingers crossed, in person soon even. So let me start off by making a claim that hopefully is not particularly controversial. We learn through interaction with our worlds and others. Well, let me say a little bit more precisely what I mean by that. I'd like to have you imagine yourself as well a toddler. So around this toddler you are a wide range of things you can play with and interact and learn from. Some, like these blocks, you can interact with by grabbing, whacking around, throwing, and toddler you, being ever curious, does all these things. And in doing so, you learn about these blocks, how to manipulate them, how to construct things out of them, how they'll behave if they collide or fall. If toddler you looks up, you might see something very different. See, this ceiling fan is dynamic. It moves in a regular pattern. You might realize that you can flick a switch and turn it on or off. If you can somehow get close enough to it, you might try to cause quite a stir by trying to touch it. Not a particularly good idea. But largely, you just watch it. And what initially might seem mesmerizing eventually becomes quite predictable. Looking out a window, you might see leaves rustling in the wind. These are really mesmerizing in that no matter how much you look at them, you can't entirely predict what they're going to do. They're quite chaotic. What you can do is try to grab them, but then the random motion magic ends. Somewhere in all these confusing dynamics are a really important class of stimuli, animate, social stimuli. These behave with considerable unpredictability, but also considerable regularity. They have goals, affect, internal states. Moreover, incredibly, our action seems to affect how they act in really subtle ways. And the skill with which we comprehend these mysterious others in our lives determines so much. This understanding is the basis by which we learn from others, cooperate, collaborate, compete, etc. In sum, we learn by interacting with our environments and the people within them. This action that we take, that is what we look at, what we manipulate, how we act towards others, affects what we experience. And in turn, with this experience, we build mental models of our environments and other people. These models are keys to navigating and learning more about our world. And early in our lives, we're relentlessly curious about our surroundings. We play and explore constantly, obsessively with our physical worlds, looking for novelty, irregularity, and at least we hypothesize, basically trying to optimize to physically understand the world. So much so that we've been called scientists in the crib. And a lot of our interactive learning early in life is social. If you've spent any time recently with a young child, you know that an enormous amount of their attention and energy is focused on others. Sometimes to try to get at some instrumental need like food or warmth or physical touch, other times really just to play, to understand the other. Take, for instance, the game of peekaboo. I bet you've not really played it in a while, but it's really a quite complex behavior, these dramatic contingencies between the parent and the child as they hide themselves, show themselves, and react. Yet, not everybody learns through interaction the same way. So meet David, the cousin of a colleague of mine. Like an estimated 1 in 59 children, he is on the autism spectrum. Many on the autism spectrum, starting very early in life, do things differently. They look at faces less, starting perhaps 2 to 6 months of age. They engage in play, both physical and social play, differently. And like many of them, David is different in how he navigates the world of affect, emotions. Affect is incredibly complex, right? We look at faces, we recognize certain patterns in them, we interpret, we contextualize in the broader social interaction, and we respond. David has trouble with this process. Illustrated here is the true story of how his family would practice with him in a bathroom mirror. We wondered, could we somehow augment David's learning by emulating this process, at least a bit of how we navigate it, in a wearable artificial device? And so we began what ended up being called the Autism Glass Project. It uses Google Glass and is powered by artificial intelligence. Since a one-on-one demo here is a bit of a toughie these days, let me just tell you a little bit about what the prototype does. So you put the Google Glass on, and it's been stripped of all its usual software. So if you're away from people, it does nothing. But here's your friend Peter. As soon as he comes in front of you, the outside light prism lights up in a green box. Under the hood, face detection is constantly looking to see if people are in front of it. Then, since Peter's smiling, it tells you so. Using a face tracker and facial expression recognition, it automatically provides feedback. And our question here was really, Could this serve as a home therapy delivery system that could teach affect navigation and more broadly provide a sort of scaffolding for socialization? A learning tool that builds skills, enabling all sorts of ways, and then when you take it off for good, you have these skills. To validate this idea, we ran a sequence of 3 studies. The first, an in-lab feasibility study, was largely qualitative. We wanted to understand simply when we gave them this sort of device, a child with autism, when we gave them this feedback, what did they do? What did they look at? How did they respond? Armed with this, we then designed a fully working prototype, sent it home to families of kids with autism, saw what happened, made some measurements, altered the device, and so on, over and over again over a period of about over a year. This also gave us a sense of how the device might be helping. So I'll read this along with you. We already noticed something very dramatic I'd like to share. Participant is looking at us when he talks through Google Glasses during a conversation, and it was noticed without glasses from his teacher in language art yesterday. It's almost like a switch was turned. Thank you, my son is looking into my face. Obviously very encouraging, and along with it, some uncontrolled collection of behavioral measures gave us some sense of what we were doing. But then we decided to validate with a controlled study. Now, recall that one of the ways we thought we might be helping was broadly to improve socialization, to provide some building blocks from which all sorts of learning occurs. And indeed, on a measure of this, we found a significant effect. Yet, another way we might be helping was directly on affect navigation. And specifically on this, we barely move the needle. So from one perspective, these are promising pilot results, which need to be strengthened with a larger scale trial. To do this, we've licensed the technology to a company it's working with the FDA currently to run the next stage. From a scientific perspective, though, results like this suggest that we have a good deal more work to do. How is this device helping? How do we measure how it's helping? So where to from here? Let's zoom out for a second. Well, what have we done? We've taken a human behavior, this attending to faces, interpreting, contextualizing, responding one that I described at the very beginning, and tried to, in a sense, mimic it in a wearable device, to take some engineered version of a piece of our cognition and design a tool that augments people's learning with a machine version of this piece of cognition, making a sort of learning tool for children with autism. But as I said, while the results were promising, we have a lot of work to do, namely a couple of big questions I'd like to identify. How do we better measure and understand how devices like these help? And how do we build better such devices? In particular, how do we build devices that adapt to their surroundings, to the individual needs of others, to personalize? Well, the answer to me seems simple. We need to embrace a certain loop, that in which a fine-grained understanding of this learning process early in life informs a more faithful artificial system. And in turn, this AI understanding gives us a more precise understanding of this early learning process. It's really part of a more general principle in which we let human learning through interaction tell us how to build better artificial intelligence, and in turn, by building artificial intelligence that learns more like we do, we hope to study and aid human learning. My group works on a number of things aimed at embracing this sort of loop, using and innovating on modern techniques in computer vision and deep reinforcement learning. In the remaining time, I'd like to tell you a little bit of how we're doing this with some example projects. You'll recall at the beginning this spectrum of different sorts of stimuli. I didn't quite give them names, but static ones, periodic ones, randomly moving ones, animate ones. We wondered, how do humans decide what to look at in order to learn? Well, we distilled these sorts of stimuli down to these kinematic essentials that would be novel for people to look at. And we've been studying how people are curious in these contexts. We just ask adults to look at the scene and we track their gaze. So what you're seeing here is a purple dot for the person's gaze. And so I'll play the video here. The balls are what are called spheros. They're these little robots that have gyroscopic motors inside and allow us to program these in these kinematic ways. So the red one is staying still. That's the static stimulus. The lower right, the yellow one is moving around in a regular circle. It's periodic. The blue one at the top left is jittering about in a somewhat random manner. And the green one is doing something interesting. So when you look away from it, it moves away out of the box, out from behind the box. And then when you look at it, it darts back behind again. So it's in essence, it's playing peekaboo with you. It's the animate stimulus. And so we just want to understand what people would look at. when they were given these sorts of novel scenes. That was on a non-clinical population of adults, and we really wanted to understand how children do it, and in particular, how children with ASD do it differently. To facilitate this in the pandemic, we've moved to augmented reality. What I'm showing you here is an AR app that instantiates these Sphero-type stimuli and allows kids to explore them in their own homes. We can deploy this to children, and so long as they have an iPhone, we can collect data of what they pay attention to. So we've been collecting data from both typically developing children and ASD children since the spring, working down to 46 years of age. And we're trying to mirror this building block of interactive learning, deciding what to look at by engineering in artificial systems. Here's a virtual environment with the corresponding stimuli, the Sphero is moving about, in which our artificial agent, the little white robot in the middle, learns. So, right, our guiding question here is, how do we engineer systems that decide what to look at in their environments in order to learn? These engineered systems, through nothing other than some measure of curiosity, preferentially attend to the animate stimuli. They'll even, again, simply through curiosity, play peekaboo with the other agent, learning how to interact with them in order to learn more. But deciding where to attend is only one building block of social learning, and we're looking at going considerably beyond this. We're looking, for instance, to build artificial systems that can learn skills from experts by curiosity-driven interaction. We're working on making artificial systems that, in trying to help you perform some task, can adapt to your style and cooperate with you. Pictured here is the overcooked environment where you, in a virtual environment, cook a meal with someone else. And we're working on making artificial agents that increasingly engage in sophisticated social play behaviors simply by being curious around their world and their play partners. Pictured here is the dark blue parent agent and the light blue child agent, and they learn how to play catch simply by curiosity. So engineering artificial social learning is aimed in part at better understanding how we learn through interaction with each other, but it's not just that. I'll leave you with one last question. With AI that learns and interacts socially as we do, what better devices and learning tools can we create? Thanks.